This video will cover section 5.5. The first definition we need is a trigonometric equation, which is it is an equation that contains a trigonometric expression with a variable such as sine of x. Okay? And the solutions are going to be the values that satisfy such an equation so that's the definition for a solution. Okay, so now some trigonometric equations, as you could see, if we look at the sine function, so here in blue we have the sine function. It is traced for us, and although it doesn't go all from negative infinity to infinity, we are implying that here with the arrows, right? We have an arrow here. We don't. Maybe I just cut the picture. But we know it does have an arrow, right? Because the domain for this particular function, it is all real numbers. So now if we want to solve an equation such as this one here, sine of x is equal to 1/2, what we are saying is that on the left side, we could have the function sine of x, and that's what you see traced in blue. And now on the right side, which is the 1/2, we could say that we have a horizontal line, which is a constant function, and that would be this horizontal line that you see here, right? So that is what an example of that trigonometric equation graphically. And so the solution is going to become all those points where those two intersect. And so if you guys recall from algebra, we went over systems of equations of one variable, right? And we had three cases. We had lines that intersected at one point, so we said those have one solution, right? Do you guys remember that? And then we had systems that had no solution, which was the case of parallel lines. And then we, of course, had the case where we could have one line and then another line overlapping, or it was the same line with the equation written in a different way. And this one had an infinite or infinitely many solutions, infinite number of solutions. So now, when we look at trigonometric equations, we're going to look at those intersection points. Even though we're not talking about a system, we're still looking about those intersection points. And if you notice, since this one, it keeps going in both directions, so it's going to keep going and going. And of course, we're going to have more of those intersection points, correct? Yes? So how many solutions do you guys think this particular equation could have? Like very big. Yeah, an infinite amount of solutions. Yes, it will, because both functions, they extend in both directions, even the constant function. However, when we look at this type of problems, we're going to be either, sometimes we will be restricted in our solutions, or sometimes we will give all solutions, in the infinite number of solutions. But we're going to, of course, we're not going to list them one by one, right? We're going to find a smart way to write them down, okay? So we're going to look at those two cases. Now, when we're solving problems like a applied problem, a word problem, we're going to consider the context of the problem. So if we're talking about something that involves time, of course, we're not going to consider the solutions that go on that graphically will be on the left side of the y-axis, right? Because we can't have negative time or things like that. So we will consider that also. So how are we going to solve the equation? So first of all, we're going to um, isolate, which you already know that means to leave by itself, right? To isolate the function on one side of the equation. So what that means is that we want to have, let's say, sine of x by itself on the right side, or cosine of x, or tangent of x, or whatever trigonometric function we have. After that, we're going to solve for the variable, and the way we're going to do that, for example, in this case, I will say x is equal to the, how do I undo sine? What is the inverse of sine? Sine inverse. So you will do a sine inverse of whatever you have in the little box, all right? So that's what we're going to do, and we start here with example 1. So we have numbers and we have expressions that contain sign, right? So keep in mind that they stay together. You cannot separate sine and x. They go together, okay, all the time. So what we're going to do is we're going to move the ones that have sign to one side and the ones that are just numbers to another side. So, Ruben, where would you like to keep the ones that contain sign, on the right or left?
On the right.
On the right. And tell me why you chose to do that.
Because 5 is the biggest.
5 is bigger than 3, right? So we know that if by moving that one across or subtracting it, it will be negative 3 sine of x. And so that is convenient because we get 2 sine of x. Now on the left side, we still have this negative 2. And the negative 1, we take it to the left side, and so that will change the operation to addition. So plus 1. And negative 2 plus 1 is negative 1. Now from here, we're almost done. What we're going to do is, what is the 2 doing to sine x? Multiplying, right? There's nothing in between them, so they're multiplying. So we do the inverse operation, and that will be division. So we get sine of x is equal to negative 1/2. Now, if you guys recall, there are two, I'm going to draw the unit circle here. And let's see, where is the sign negative? Which quadrants? 1 and 3. No, negative. Not 1, 2. No. 3 and 4. The sign is negative in 3 and 4 because remember that uses the y coordinate, and the y's are negative here and here. Remember that. Don't forget. So we're going to have 2 solutions. One of them will come from here, and one of them will come from here. All right? So if you guys recall, the sine of 30 degrees is 1/2, right? Isn't it true? What would be 30 degrees in radians? Pi over 6. Pi over 6. Okay. So we're looking for something that could have the same reference angle as pi over 6, but we're actually looking for the angle that goes from here to here. What will that angle be? It is pi over 6 past pi. In radians, let's try in radians. So if this is 6 pi over 6, and you go another pi over 6, what would you get? 7. Very good. So one of them, we will have negative 1 is equal to sine of x. So we take the sine inverse of negative 1/2, and that will be 7 pi over 6. Now let's look at the other one. And so the other one is going to be that angle that goes from here all the way here. What will that angle be? I want you to think that this is 2 pi or 12 pi over 6. So then we are 11, right? Because we are pi over 6 before we get to 12 pi over 6. So that will be 11 pi over 6. Is that a cell phone? Okay. So we have negative 1/2 is equal to sine of x. So then x will be equal to the sine inverse of negative 1/2. And that will be 11 pi over 6. Okay. However, if we look back at the question, it was find all solutions, okay? So when they say all solutions, we are gonna have to somehow represent the infinitely many solutions, okay? So do you guys remember what is the period of pi, of that function? 2 pi, right? It repeats every 2 pi. So my first solution will be 7 pi over 6 plus 2, let me see what, we're going to use n pi. What does n represent? When n is equal to 0, it will just be 7 pi over 6. When n is equal to 1, it will be 7 pi over 6 plus 2 pi. So that will be 19. And so on. Okay? But with us using this, that right there, we're implying infinitely many. We will also, well, we are assuming that n is an integer. Okay, now with the other one, the other solution that we have, we will list it like this. 11 pi over 6 plus 2n pi. And it will be similar to the case that we have. Okay? Do we have any questions about that? Please ask me. Yes. If the question is all the solutions, yes. But we're going to do others where we will be asked just to find the solutions from 0 to 2 pi. So you have to be careful when you read the question. Do they want all, or do they just want specific ones? Okay? All right, so let's go to the next slide. So this is how you will represent all solutions. If we were not talking, okay, let's say if our equation, a trigonometric equation involves cosine, what will be the period that we use to represent all solutions? 2 pi or pi? Pi. No, cosine is also 2 pi. What would it be for pi? I mean, I'm sorry, what could we use pi for? Not secant. Tangent. Tangent. Yes, what were you confused about? Tell me. Let's try. Oh yeah, so this is like an example. I just did it to kind of show you what this means right here. So when we make this n be a 0, it's like we have the following. 7 pi over 6 plus 2 times 0 pi. So since that cancels out, that's why the answer is just 7 pi over 6. But if n is equal to 1, what we're saying is, let me erase this. It will be 7 pi over 6 plus 2 times 1 pi. So what I did was 7 pi over 6 plus 2 pi, which turned into 6. It will be 12 pi over 6. And so that will give me the 19 pi over 6 that I have. Okay? So it was just a little example, but I skipped this whole step. I just gave you guys the answer. That's why it looked confusing. Anything else? No? Okay. But this is not necessary to do. I was just doing it to show you guys where they come from. Okay? This right here, that's enough to imply that you have infinitely many. All right? So let's move on to the next slide, guys. And so here, okay. So now if you guys for example 2, we don't need to find all solutions. Now we're just going to find the solutions that are between 0 and 2 pi. Okay? So we will not use that 2n pi at the end to imply infinity. So what we're going to do here, we have our equation. And so tangent of 3x is equal to 1. And so here you have to keep in mind that 3x it goes together, okay? So we cannot really say divide by 3. So what we need to do instead is say, take the tangent inverse. And so you know if you apply tangent inverse here, it will cancel, right? So that is what we do, except that I just don't write it that way. The way I write it is 3x is equal to tangent inverse of 1. Because I already know that they're going to cancel over here, tangent and tangent inverse, because they will undo each other. So anyways, it's the same thing. I have 3x and I have tangent inverse of 1. Same thing I have here, right? Yes? Do you guys see that? Okay. So now from here, you have to think about where is the tangent positive, first of all. In quadrants, what? 1 and 3. So it could be something here or something here, right? So what is this angle right here, guys? Where the tangent is equal to 1, yes, it is 45. Since here they're giving us our restriction in radians, let's give our answer in radians. So then we will say 3x is equal to pi over 4. Or, what is this angle right here? It will be pi over 4 past pi. Pi over 4, very good. Okay. But you guys notice how the angle is still 3x? Okay. Now I can divide by 3. And so I will say that divided by 3. So it will be x will equal pi over 4 divided by 3. And so that is equal to pi over, what is 4 times 3? Well, 12. Pi over 12. For this one here, we do the same thing. Divide by 3. And we will get 5 pi over 12. So now I want you to think of something. 5 pi over 12, where will that angle be? Well, the terminal side of that angle, where will that be located at? In which quadrant do you guys think? 4. 5 pi over 12. No. It will be in 2 because it's less than 12 pi. Actually, it will be in 1. Did anyone say 1? My bad. It should be 1 in quadrant 1. So what that tells me is that we're missing several answers here. We're missing so many of them. So this is a trick. And you might find that this annoying on your homework. But I'm showing you what to do, okay? So don't complain. What we have to do is use that little form that we used before. Let me write a little smaller. In fact, I'm going to make more room for myself. So we had one of our solutions was 3x is equal to pi over 4, right? And then the other one was something like 3x is equal to pi over 4. Thank you. Okay, so what we're going to do here is we're going to consider that plus 2n pi. I know we're saying that we only need a certain number of solutions, but trust me, this will work. So we add plus 2n pi to both. And then we divide by 3. Okay? So then we will have x is equal to pi over 4 plus 2n pi then everything divided by 3. So the way we reduce that is going to give us pi over 4 divided by 3, and then of course 2n pi divided by 3. And so I'm going to reduce it again. So we will get pi over 12 plus 2n pi over 3. Okay, so go ahead and you guys do the next one, and then we'll compare answers. Okay, now in the previous question, since they were asking us for all solutions, we didn't really limit the value of n, right? In fact, did we even say anything about it? For n is an integer, right? That's all we said. N could be as big or as small as you want. However, for our other problem that we have here, we cannot let n be whatever it wants. We still have to keep n within this range. Okay? So let me tell you what I mean by that. So get your calculators. And I want you guys to add.
Does the calculator have to be read?
No, because we're just using pi, so it will be okay. So I want you guys to add the following. So make your n equal to 1. So add pi over 12 plus 2 pi over 3. So in this case, actually my first solution is pi over 12, right? So now you will add pi over 12 plus 2 pi over 3. Because I'm making n equal 1. And if you have a black calculator, it should give you the reduced form, right? What do you get, Sandra? 3 pi over 4. Is that still within this range? Yes, it is, right? Okay, let's try it again. So now we're going to make n equal to 2. So you guys are going to add pi over 12 plus, right here, look at the board. This n will be at 2, so what will we have? 2 times 2? So 4 pi over 3. So add that on your calculator, please. And then tell me what you got.
17 pi over 12.
17 pi over 12. Is that still within here? Less than 2 pi? Yes. Right? Okay, now let's make our n equal at 3. So then we will have 2 times 3, that will be what? 6. Okay. So let's add pi over 12 plus 6 pi over 3.
Pi over 12.
What is it? Say that again.
25
pi over 12.
25 pi over 12. So that one is out of this range, right? It's a little over. Precisely pi over 12 over, right? So then we stop there. This will not be one of our solutions. So we're good there. Now let's look at the ones in green. So we start with, of course, making n, this n 0. So it will just be 5 pi over 12. Now let's make your n equal to a 1. So you will be adding 5 pi over 12 plus 2 pi over 3. Remember, this n here is a 1. This n is a 1. What do we get? 13 pi over what? What?
12.
12. Okay. We're still good, right? Is less than 2 pi? Yes, yes it is. If we get past 24 pi over 12, that means we're past 2 pi. All right, so let's do one more. So now we're going to make this n equal to 2. So that means we're going to be adding 2 times 2 is 4, so we're going to be adding 4 pi over 3.
7 pi over 4.
We're still okay, right? We're not outside the 2 pi. And now if we make n equal a 3, think about it. That will make this n be a 3. So 2 times 3 is 6. And isn't it true that 6 pi over 3 is equal to 2 pi? So isn't it kind of like a red light that, hey, you're already adding 2 pi, so you are going to go over 2 pi. So once you get something like that, you could stop. If you're not so sure, it doesn't hurt to check and see what you get, right? But I can promise you that if you do this computation, you will get something over 2 pi, okay? Just try it. Go ahead and type it in. 5 pi over 12 plus 6 pi over 3. 29 pi over 2. So you're way over 2 pi precisely by what? 5 pi over 12. Very good, very good. Do you guys see how important fractions are? Do you see this one? I do. Okay, so next question. Okay, and so I warn you that on my math lab, you might have a few problems like that. That you might be just giving like the first 2 solutions and it might be telling you it's wrong, it's wrong, it's wrong. And it doesn't mean that your first 2 are wrong, it just means that you're missing others, okay? So sometimes what I could recommend that you do is that you graph, you could do this to check your work. You could graph this and then you could graph that, like 2 separate equations. One of them could be like tangent of 3x, and the other one could be y equals 1. And so you graph them and you see where all those intersection points are happening between 0 and 2 pi. That could give you a good idea, all right? But if my math lab is asking you for an exact solution, you have to get your solutions in terms of pi, just so you know, all right? So let's go to the next equation. So right here, we have sine of x over 2 is equal to the square root of 3 over 2. Again, we want to keep it between 0 and 2 pi. So we're going to use the sine inverse. Square root of 3 over 2. And then I want you guys to think about this. So let's see. Where is the sign positive? Let's think about that first. Quadrants 1 and 2. Okay, so so quadrant 1. So that one, remember, it's not pi over 6, it's the other one. What is it?
Pi over 3.
Pi over 3, right here. And the other one is going to happen here. And that angle will be, it's not 3 pi over 3, 2 pi over 3. Very good. Okay, so those are our two solutions. So one of them will be x over 2 is equal to pi over 3. And just so you know what will happen, I'm going to go ahead and add that 2n pi. And the other one, the one with the red angle, will be x over 2 is equal to 2 pi over 3 plus 2n pi. Now you could see that the 2 is doing what? What is it doing, guys? To the x. Right here, this 2. Dividing. So if we want to isolate x, we are going to multiply, right, by 2. Take this 2 across, and we'll do the inverse operation, and so it will be 2 times all of this. And then we distribute the 2. And so, do you guys see what's going to happen when I multiply 2 times 2n pi? What am I going to get? 4n pi. So if we only want solutions that don't go past 2 pi, would it even be worth for me to try to add multiples of 4 pi? Maybe not, right? Because I'm going to go definitely the first time. Oh, well, if n is 0, of course, that's the only one that will work. So this one only works with n equals 0. And so you will get x is 2 pi over 3. Now with the other one, we have that. And so we will get x is equal to 2 times all of that. So 2, remember right here, we only multiply numerator times numerator, so that would be 4 pi. Denominator times denominator, that would be 3. And here it will be 4n pi, so in reality, again, only works for n equals 0, so the only solution will be 4 pi over 3. So how many solutions do we have here? 1 and 2. 2 solutions. How many solutions we had on the previous one? 6, right? Remember, 1, 2, 3, 4, 5, 6. Okay. Next problem. What happened here? Oh, okay. Now, sometimes there are like a few little tricks to this, and one of them is that you have to use some factoring techniques, okay? So let me refresh your mind on those. So we have one thing called a trinomial square, right? Such as that one. And so we're going to have to be factoring things. And the idea that we're going to use is that we are going to be considering, in this case, cosine x, it will be like equivalent to u. And so cosine square x will be equivalent to like u squared. And then we have a 2 here. And then here minus 1. So that is what they're showing us here. I'm just writing it again because I know it's tiny on your paper. So we're going to factor it in that form. So if we had an equation such as that one, 2u squared plus u minus 1. We could solve that by factoring. And so it will be 2u and u. And we have negative signs here, so that implies that we have one of each inside the binomials, right, in the middle. So my guess is that the positive goes here and the negative goes here, because we end up with a positive in the middle. So the only factors of 1 are 1 and 1. Let's see if this works. So if we multiply 2u times 1, we will get 2u positive. And if we multiply negative 1 times u, we will get negative u. If we combine those, we get positive u. which is the term that we needed in the middle, right? So now we're going to translate that. We're going to use those factors that we have here and translate those into this form of the equation, all right? And so that will be 2. Instead of u, we're going to have cosine x minus 1. And the other one will be, instead of u, we will have cosine x plus 1. And that is equal to 0. Now from here, we're going to use that zero factor property that we use so much when we were finding zeros with polynomials. Do you guys remember that? So what am I about to do? We're about to equal each factor to what? 0. So again, we're going to have 2. Now we're having 2 equations. 2 cosine x minus 1 is equal to 0. And now we're going to solve for x, so it will be 2 cosine x is equal to positive 1, right? I took that negative 1 across, negative positive 1. And now what is the 2 doing to the cosine? Multiplying. So we need to do what? Divide. Okay, so right there. Let's work on the other one. So that will be cosine x plus 1 is equal to 0. So cosine x is equal to negative 1. And then from there, now I'm going to solve them. So x will be equal to the cosine inverse of 1/2. And here I'm going to have x is equal to the cosine inverse of negative 1. All right, so from here, we're going to have 2 solution sides again. Okay? So think about it. Where is the cosine positive? Quadrants 1 and? No. 3. No. 4. Come on. So we're going to have one of those here. And that angle is pi over 3, or 60 degrees. We're also going to have another one here in quadrant 4. And so it goes like this. And that one is pi over 3 before we get to 2 pi. What would that be? This one is 6 pi over 3. So I heard a 5, yeah? 5 pi over 3. Very good. So 5 pi over 3. Remember? 6 pi over 3 minus the reference angle. Okay, so we got 2 solutions there. And now let's go for the other equation, and that one is going to give me 2 as well, or just 1. What do you guys think? Where is the cosine equal to negative 1? Can I remind you cosine? You can use the x coordinate. So think about an angle. That will be tangent. Well, we want our angles to be between 0 and 2 pi. So we want them to be positive and less than 2 pi. So, all right, I know you're going to remember as soon as I do this. Possible. So where is the x equal to negative 1? At pi. That's it. There's nothing else that has a cosine on negative. Unless we add 2 pi, but then we will be over 2 pi. So we don't want to do that. So how many solutions do we have now? 3. 1, 2, 3. All right. Very nice. When you enter your solutions, make sure you read the instructions. Like, they might want you to separate them with a comma. They might want you to put them inside the curly brackets. You don't know, okay? So, of course, you look at the examples. Make sure you enter your answer correctly. Yeah, how about we take a break? You guys want to take a break? Okay. So let's move on on to example 5. I'm going to show you 2 ways to solve this one. One way is by factoring as the difference of squares, okay? And then you guys can choose whichever way you prefer. And so when I say factor as the difference of squares, what I mean is this. So 2 binomials. So the square root of 4 is 2. The square root of sine squared is sine. So sine x and sine x. And then what is the square root of 1? 1. So we'll have a positive 1 and a negative. From there, you already know you take each factor. You equal it to 0. So 2 sine x, first we take care of the positive 1, turns into a negative 1. Then we divide by 2. And the other one is 2 sine minus 1 is equal to 0. Oh, I say sine x, sorry. So then 2 times sine x is equal to positive 1. And then we divide by 2. So if you guys notice here, we're going to get, how many solutions do you guys think? Within this 0 to 2 pi, how many solutions? Love it. 4, right? Because sine is positive in quadrants 1 and 2, and then it's negative in quadrants 3 and 4. So I want you guys to think about those angles. Okay, you're going to get 2 from here, and then 2 from here. So think about it. You can discuss with your partner. Okay, so from here, I'm going to do the positive ones. My favorite angle, pi over 6, right? What else has that? It's got to be in quadrant 2. 5. Very good. And then negatives, it will be past pi. What would that be? 7. And then the other one will be pi over 6 before 2 pi.
11 pi over 6.
Good job. Good job. All right. The other way that you can solve it, I'm just going to show you how to set it up. The answers obviously will be the same, right? So this is what you could do. You have your equation. You could first take care of this negative 1 by taking it across. Of course, it will become positive 1. Then you will divide by 4, right? And then how do you undo a square?
Square root.
Square root. So right here, you will have the sine of x is equal to the square root of 1 over the square root of 4. And so we know that the sine of x is equal, the square root of 1 is 1, or plus minus 1. And the square root of 4 is 2, or plus minus 2. So right here, what we're saying is the same thing that we got here. Positive 1/2 and negative 1/2. You guys see? Okay. So, I mean, either way is fine as long as you don't forget when you take the square root that you have to a positive and a negative. Okay? All right, next one. So we're going to use factoring on this one. Okay, so let's go ahead. Before we use factoring, what we want to do is equal one side to 0. All right, so I want my right side to equal to 0. Well, actually, no, I want my left. What do you guys think? I changed my mind. And don't say because women are difficult. Because 3 tangent x is bigger than tangent x, right? Yes. Okay. So we do that, and then we take this whole expression to the right side. So instead of having a plus sign in front of it, it will have a negative. So negative tangent x times sine square x. Okay. Now, those two terms, and I say 2 because there are only 2, right? Separated by the negative sign. Those two terms have something in common. What is that thing in common? Tangent x, right? They both have it. So what I'm going to do is factor that out as if there was the GCF. Well, in fact, it is the GCF. So the greatest common factor. So tangent x, you factor it from that expression, and so you will get a 3 minus sine square x. And so again, we use the zero factor property here, and we take each factor equal it to 0. So we have 0 is equal to tangent x, and then here we will have 3 minus sine square x is equal to 0. Okay, so of course we know that we need to do the tangent inverse, right, of 0 to get x. And so think about those points again. So if you think about tangent, what will be the identity that we could use for tangent, the quotient identity? Will be sine over what? Cosine. So the idea here is that the tangent will be 0 anytime the sine of x is 0. So at which angles is the sine 0? Because if we have 0 over 1, it will just be 0, right? So where is the sine 0, you guys were saying?
2 pi and pi.
2 pi and pi? There's one more, no?
No.
How about 0 degrees or 0 radians? 0 radians, pi radians, and then 2 pi radians. So we have 3. But let's look at our interval, and if you notice, right here, we have greater or equal to 0, so that means we are going to include 0. This is the tangent value, okay? This is the angle. Don't get confused with the 2 zeros. So 0, because 0 should be part of it, it's included. And then we have pi, and then should I add 2 pi? No, because here we're just saying less than 2 pi. So 2 pi will not be part of the solution. Now let's solve the other one. So we have 3 is equal to, I'm going to take this negative sine square x to the other side, so it will be positive. And how do we undo a square? Square root?
I have a question.
Yes.
Wouldn't 3 be negative 3 if you move it to the other side?
Oh, the one we moved was this one.
Oh.
Yes. We could have done that too, but then it will take us an extra step to multiply by -1. So we do that, and then we will have that x will come from the sine inverse of the square root of 3. That will be x. And now that one is not one of our special angles. So we're actually going to have to use the calculator, okay? So can you guys please type in sine inverse of the square root of 3? And then tell me what you get. Oh, how could you? I'm just kidding. It is undefined. I'm just kidding. Okay, now I want you to give me, guys, an approximation of the square root of 3. Just type in square root of 3, control enter. What is it?
1.73.
1.73. And so, do you guys remember that those waves that we spent so much time doing? Right? What was the amplitude of that function, the sine function? 2 or -1 to 1, right? So what that means is that this 1.73 is outside our range because it's bigger than 1. So that's why your calculator is telling you undefined. So that will be the answer for this. So how many answers do we have? Only 2. Okay? Only those 2. Any question? Okay. So next. Again, factoring. Oh gosh. And then what's after that? More factor. Okay, let's try to do this fast. You guys are getting pretty good at this. I think we can pick up the pace a little bit, right? It looks like 20 to me. It's 11:40, 15. Okay, so that one is. Oh, I'm wrong. Okay, so let's see. Right here we must use an identity to solve that. And so we're going to refer to the Pythagorean identity. So sine square x plus cosine square x is equal to 1. So I want to solve for cosine square x, and that will be 1 minus sine square x. So what I'm going to do here is substitute cosine square with the expression that I found here. So 1 minus sine square x. And then we will have plus 3 sine x is equal to 0. Then from there we need to distribute the 2. So we'll have 2 minus 2 sine square x plus 3 sine x. Now it does look like a polynomial, right? Doesn't it? Yeah? But instead of x we have sine x. So I'm going to rearrange it. So we will have negative 2 sine square x plus 3 sine x plus 2. And now since I want to factor it, I'm going to multiply everything by negative 1. So we'll have 2 positive 2 sine square x minus 3 sine x minus 2. And what is 0 times negative 1? It's still 0, right? So that's a trick that you could always use. Multiply the whole thing by negative 1. Okay, after that I'm going to factor it, and so the factors are going to be 2 sine x, and we will have one of each on the signs, a positive and a negative. And so I'm going to guess that the negative goes here. We'll have a 2, and we'll have positive 1 here. After that, of course, we need to use the zero factor property. And so that will be 2 sine x plus 1 is equal to 0. And then sine x minus 2 is equal to 0. So we solve each individually. So 2 sine x is equal to negative 1. That makes sine x equal to negative 1/2. And so x will be the sine inverse of negative 1/2. And so in that case, we already have the solutions for that, right? What would that be, Sassini? We have them on the previous page. You think? Right here. 7 pi over 6 and 11 pi over 6. Okay, the next one, this is easy because we will have sine x is equal to 2. And we already know that the sine of x, if we're talking about the parent function, is not going to go past 1, right? So if we enter that on the calculator, we're going to get an undefined answer or error. So our only 2 solutions are those 2. All right. Now the next one that we have here, we're going to have to use the formula for a double angle. Okay, so what I'm going to do right now, while I look for that formula, I'm going to pause the video and pass your exam so you can take a look at it. So we do have 3 variations of the cosine of a double angle identity, right? One of them, well, actually, we have it there on the board. One of them is cosine square of x minus sine square of x. Another one, it is the 1 minus, let me just make sure it is minus.
1 minus cosine squared of beta.
No. Wait a minute. Oh, I'm looking at a different problem. Sorry. You were right, Kimmy. Tell me that again.
1 minus 2 sine squared of x.
of x, right? Or theta if we were talking about theta. So in fact, and there's one more, and that other word, I believe it's like 2 cosine squared x minus 1, something like that. So the one that we're going to use out of this 3 is going to be the second one, the one in the middle. Why do I choose to use that one? What do you guys think? What do we have here next to the number 3? Sine x. So that's why. Okay? So instead of cosine of 2x, we're going to substitute it with 1 minus 2 sine squared x plus 3 sine x minus 2. Now I'm going to go ahead and rewrite it. So negative 2 sine squared x plus 3 sine x minus 2. And so from there, multiply by negative 1 again, like we did previously, just to take care of this negative sign, because it bothers me when I factor. Oh, and that should be a negative, right? The next term should be negative 3 sine x, and then a plus 2. Okay, now we're going to factor it quickly. And so we will have 2 sine x. Here we have both signs will be the same, and both of them are going to be what? Right here. Negative. 2 only has 2 factors, 2 and 1. My guess is that the 2 goes here and the 1 goes here. Let's check. 2 sine x times negative 2 gives me negative 4 sine x, and then negative 1 times sine x will give me negative sine x. Oh, that's not going to work, huh? Okay, so that's negative 5 sine x. So what does that mean?
They're backwards.
All right, so let's switch. So that was a bad guess. So the 2 goes here and the 1 goes here. Let's see if it works now. 2 sine x times negative 1 is negative 2 sine x. And then negative 2 times sine x is negative 2 sine x. Uh-oh. We're in trouble. What's happening? This is negative 4 sine x. So what does that mean? That this is not factorable. Oh, no. So what do you guys think we're going to have to use?
The other one, the
Quadratic formula. Yes. So give me a second.
yeah.
Okay, so I made a big mistake here, guys. So the one, this one right here, somehow I forgot to combine it with this minus 2. And so 1 minus 2, what is 1 minus 2, guys? Negative 1. And so then after that, this should be a positive 1, right? Okay, well that's good news. We can factor maybe. So we don't have to use quadratic formula. So 2 sine x, and then we have minus, right? And factors of 1 are just 1 and 1. And yes, of course that will work. 2 sine x, negative 1 sine x, or negative 3 sine x. That works. Okay, so I'm going to finish this problem really fast. And then we will stop here. So 2. Can someone get that? So I'm going to take each factor and equal it to 0. We get 2 sine x. Don't open the door. Well, if you already did, don't worry.
Nope. 2 comments right when you did.
Okay, thank you, Lisa. So sine x is equal to 1 over 2. And then after that, we have to do the sine inverse, right? So sine inverse of 1/2. And that one we should know already. It is pi over 6. And it's also, what else? And what else? 5 pi over 6. And from here, where is the sign positive? We're talking about the y coordinate, positive 1 right here. What angle is that? What? 90 degrees, and we're in radians? Very good. Okay, so this will be the end of this video. We'll finish this on Friday, guys, okay?